All right. Now, let's talk about the non-ideal scenario. In the theoretical yield scenario, notice that every single question that I listed a reactant, I never talked about the other reactant. Unfortunately, or fortunately, in the real world, you need to know both, because there's very few times in a laboratory setting where you're going to have an extreme amount of excess. So if you do not have excess and you want to know how much is going to be formed, you must determine what is known as the limiting reactant. And the limiting reactant essentially is what runs out first. What runs out first? Which reactant runs out first? And you can again check your text for that specific definition. How do we approach a limiting reactant problem? We must determine what is limiting or what runs out first. Very quickly, to be able to tell a limiting reactant problem, the hint, they're going to give info about both reactants. When you see info about both, you immediately know that it's a limiting reactant problem. If you see info about one, you're over here in theoretical yield. And to determine limiting reactant, you must compare reactants. And we can compare them stoichiometrically using dimensional analysis.
It's a different way of what we just did before?
It's the exact same process, but we must know how to compare the answer. We must know how to compare the final data, the final number that we get from the math. But we have to be able to compare those reactants stoichiometrically, which means that we have to form two-dimensional analysis to do this. And there's very important, this is a very important point here, that the product that you are using to compare the two reactants must be the same product if there are multiple products. And we'll show what that means here. All right. The reaction that we see here. CH4 is methane. O2 is oxygen. The type of reaction. Combustion. This is that's the easiest one to know. Combustion. O2 off the rip. Hydrocarbon, oxygen is a combustion reaction. Therefore, our products, if we were to have to predict them,
Carbon dioxide.
CO2 gaseous plus water gaseous. Reaction is predicted products, predicted cool. Balanced. No. Balanced now? Yes. Remember, I don't write these when I'm writing up here, but you can if it helps you. These are assumed ones. You can write them all you want to. It's not wrong if you put them, if that helps you. All right. Now, as it pertains to these kind of questions, you have to be given data about both. So let's look at mole to mole question utilizing limiting reactant. A tells us 17 moles of CH4 is reacted with 9 moles of O2. How many moles of water formed? All right. Structure of the question, almost identical as we saw before. Only difference is now we have information about both. We cannot make the assumption that we made over there that we have excess of reactants. We have to figure out which one of these is going to run out first, and that has implications on how much product is formed. Whoever runs out first is what dictates how much product is formed, right? Okay. We must set up two-dimensional analysis, one for each reactant. Let's start with the first one that they give us, 17 moles of CH4. We are looking for moles of H2O formed. So what does our dimensional analysis conversion factor look like here? Which one are we going to use? Mole to mole. And what would those numbers be?
Bottom is 2 moles of H2O.
The bottom is
1 mole of CH4.
has to be the same unit. Always. 1 mole. CH4. Top.
2 moles of water.
2 moles of water. This is a mole to mole. Do we have any more steps after that? No, this is not a multi-step. This is a one-step. This number, 34. All right. We now need to do the exact same calculation using 9 moles of oxygen. Using mole-to-mole conversion. And in this case, we get 2 moles of O2 for every 2 moles of water. The number is 9. And I'll give you a second to copy that, because what I say next is the most important thing I'll say about this. Ding. Round 1. Wait. Y'all too young to remember that. They still say that? In the new game, though?
Yeah.
They do? I haven't played it. I came across the arcade game not too long ago. I had a blast.
Yeah, the new one's not too good.
I can't imagine. Nintendo and Super Nintendo getting blisters. Y'all don't remember those days. I remember those youngins. My hand hurts. You stop playing a video game. Me and my cousin, we played. Try to beat that second Ninja Turtles game in one day. Tough. All right. So we have now both reactants, both theoretical yields. That's what both of these are. These are theoretical yields mathematically. Why? We haven't taken into consideration one or the other. We have not compared them yet. We're about to. But before we compare them, we've effectively done a theoretical yield for 2 different reactants. But since we know this is all we have, then this becomes a limiting reactant problem because we have 2 different amounts of products. They're not the same. You could have a reaction where these numbers will be exactly the same. Then everything is consumed at the same time. Both things are gone. But now we see that if we used all of the methane, then we would get 34 moles of water. But if we used all of the oxygen, we could only get 9 moles based upon the balanced chemical equation. So, when you are comparing reactant that leads to least amount of product is limiting reactant. Very important. That is the key. When comparing the number of moles of product formed, the reactant that leads to the least is the limiting reactant. And normally you'll see me label this with an LR. So I'll write LR near the reactant. A lot of people make the mistake and write the limiting reactant next to this product. The product is not a reactant, it can't be a limiting reactant. You're concerned with the reactant that led you to the smallest amount of product. O2 runs out first, effectively, meaning that O2 is going to give you the least amount of product.
I have a question.
Uh-huh.
So do we write the 9 or do we just write the O2?
The limiting reactant is just the O2.
O2, okay.
Yeah, the amount of moles is not really concerning the limiting reactant. You just write that O2 is going to be limited. Now, let's say that I ask the follow-up question to this. Well, the second, to be able to answer this question, you must determine limiting reactant. Then, how many moles of H2O formed? Is this value. This is the answer to our question. Because it comes from a limiting reactant. There's your answer.
So the lowest number will be your answer.
Lowest number will be your answer.
So 34 is not even.
Well, you need to calculate 34 to be able to compare, but 34 is not the answer because it is the larger amount. This is this star right here. Product compared must be the same. You cannot do the dimensional analysis here and look for moles of water in one and look for moles of CO2 in the other. Can't do that. That's where people sometimes might make a mistake. You have to use the exact same product. You could have used CO2 if you want to. You just got to use it in both places. Got to use it in both places. It's still going to give you one larger than the other, and it's still going to give you limiting reactants. But you have to pick a product and stick with it. Which one? Doesn't matter. Which one doesn't matter. All right. Let's go mass to mole. .0 grams of oxygen reacted with 112.0 grams of methane. How many moles of CO2 formed? All right. We have two masses. Your brain should immediately say, okay, well, we're going to have to convert from mass to do anything. Because we don't work in mass around here. It's like going to another country and trying to just make it rain American dollars. It's not going to work. We don't take those here. All right. Can we determine, looking at these numerical values, a limiting reactant before doing any math? Can we look at them and tell? Can we say, 92 is smaller than 112? No, don't do that. You cannot do that. You need to do the math. You need to set up the dimensional analysis. Here, the dimensional analysis is that of the type that we talked about in part B. Over there, we must go from moles, from grams to moles to be able to compare moles. So, 92.0 grams of oxygen, and our next conversion factor must be of the type molecular weight. You need to use molecular weight. Oxygen is not 16. A lot of people make a mistake and write 16 down here. This is O2. 32. A lot of people make that mistake. 32 grams of O2 per 1 mole of O2. Remember, this is a two-stepper. The question is given us the product of interest. I'm going to show an example where we don't. But in this case, the product of interest is CO2. So for every 1 mole of CO2, there are 2 moles of O2. Remember, this comes from balanced chemical equation. This comes from molecular weight periodic table. Now, we know how many CO2 is formed. Record. All right, cool. Just make sure it's recorded. Mm, 64 to 92, about 2/3. What is it? Point what? 6?
4.4.
Oh, yeah, 2/3. No, not 2/3. 1.4. All right, 1.4 moles of CO2. All right. This is not the answer to our question. This is not the moles of CO2 formed. This is not enough for us to answer the question. We must do the math for methane. 112 grams of CH4. And we can emulate this exact same setup. Obviously, the numbers are going to be different. 1 mole of methane is 16.05 grams of methane. And for every 1 mole of CH4, we have 1 mole of CO2. About 8, what is it? 7, 8? 6.98. 6, so pretty much 7. 6.98. All right, well, a visual inspection will tell us which one is the smaller value here. Therefore, oxygen is our limiting reactant. Therefore, the answer to our question, given the parameters in the question, is here.
Do you want us to show you both equations, even though, if, for example, I know which one's basic in the question?
Okay. I am going to be asking you to write out the work because there's going to be points associated with it. Just because you have enough math sense to be able to say, yeah, based on the molar mass and based on the amount and based on the stoichiometric coefficient, that's good. That means that you should never get one of these wrong.
I'm saying comparing them. Like if I know the O2 is limited to 1, I'll do that math.
But you can't know beforehand. That's my point. To be able to know beforehand means that you have enough math sense that you should never get these wrong and you should get all of the points associated with it. What I'm saying is that if you've done this math in your head, then it should be no problem for you to write it down. That's what I'm saying. Most people can't be able to say, okay, 112, then take the molar mass, then do a division and realize that this is 1. There's plenty of places to make pitfalls and mental mistakes there. But if you can do that, then that means that you should never get a mass stoichiometry problem if that is in case of fact. If that is in fact the case. Most people can't. I was in graduate school and had 8 years of chemistry experience, and if you looked at my graduate notebook as I'm making solutions, you will see dimensional analysis written out just like this. You must, I mean, it's just the safest and best approach. Any questions about A or B? Because I'm about to race these.
If this question were to be on the test, can we just, for the answer, can we just square it instead of just like rewrite it? Like if we were to do.
Oh, right. I'll probably give you a blank or something, or I will say circle the limiting reactant. Yeah, something like that. Circle the limiting reactant, circle the answer, something like that. Yeah. You don't have to necessarily write 1.4 again, unless it might be a blank. Because a lot of times what happens in this test is people write a bunch of just mess and hope that something they wrote down is right, and I don't go searching for answers. That's not me. This is not a philosophy class. C and D. Well, I'll leave that. All right. Mole mass. .44 moles of CH4 reacted with 2.38 moles of O2 determine limiting reagent. Reactant. You'll hear me say reagent too. Same thing. Reactant, reagent. Again, question posed to you. Oh, well, there should be a second part to this because we want to go mole mass. Determine limiting reagent and mass of a product. So I'm leaving it a little open-ended. Kind of, you got a choice here. So determination of a limiting reagent you can't do without comparing products. And the product you compare is up to you. It's up to you. So the math here will start with moles. 0.44 moles CH4. We're already in moles. We can go directly to mole-to-mole conversion of the product of interest. We just did CO2. Let's use water. We'll use water. 1 mole of CH4 for every 2 moles of H2O. We want to get a mass of a product. That's what the question is asking us. But do we have to get the mass of the product to determine limiting reactant? Can we mathematically